What I'll be speaking about is not only my work. I try to do some overview of this topic, geological record of recent climate change on Mars. Mars is a beautiful planet. It's a unique planet. It has active geological processes. From formation of the planet till now, it is active all the time, but it is not too active. So we see traces of these processes through the whole history. So,
excuse me, sorry to interrupt the speaker. We unfortunately are not allowed to put additional chairs.
it's on.
Fire safety restrictions. So I was hoping to find chairs.
Okay, then maybe I guess just speak up a little bit if
And
that's all right.
please, while we're interrupting, please, if you'd like to come, there's a chair here, there are one or two chairs here, and feel free to come sit on the floor if you'd like. So. Oh, there's a chair here. Jenny, there's a chair up here if you don't want, or. Maybe raise your hand if you're next to an empty chair. You guys okay? Okay, go ahead, sorry.
Okay, so this kind of scheme of geological history of Earth, Moon, and Mars, and for Earth we have good record for only this part of the history. We have some materials from this part, but not a complete intact record. For the Moon, this part is pretty boring. Little happened here, and we have a good record of this part. For Mars, we have everything. We see all of these from now to early days. Usually people like to deal with early days because it's supposed to be warmer, wetter, more interesting. I will focus on this more or less equivalent of known geological record on the Earth, late Amazonian in Martian history. In this time, most things that shape the surface of Mars are related to climate. Migration of water ice from place to place, winds, and things like this. So geological record here is actually a record of climate changes. And I will overview what forces change the climate are responsible for formation of Martian climate. I will show some examples of what we see in geomorphology, and I'll try to reconcile one and the other. So this table, okay, do you hear me? This table shows a list of different time scales related to Martian climate system, the whole system. So the shortest is daily cycle, and so there is certainly years, seasonal cycle, and so on. The longest is transition from early Mars to the present day Mars, with many things changed. So this is the whole list of climate time scales, and we will deal with intermediate. So year-to-year variability, it is kind of weather, it is not climate. So there are 4 items here. It is internal instabilities of the climate system. It is some speculative variability of the sun luminosity. It is astronomical climate forcing, meaning change of orbit and spin of the planet. And there are some discrete catastrophic events like large impacts, large volcanic eruptions, and so on. So let's start with the most uncertain one, sun variability. We are used to think that sun is not a variable star. Its luminosity is pretty constant. It is well measured for the last 2 solar cycles, and it is constant. Its luminosity has detectable variations along 11-year solar cycle, but these variations are very small. Certainly we don't have direct observations of solar luminosity with enough accuracy for times longer than a few decades. There is some work that speculates about this level, 0.25% level of decrease of luminosity in 1650, 1750. I don't believe in their logic. Maybe they are right, but I don't believe in their logic. But there are some opinions that this is possible. Terrestrial geological record cannot help in this. There are certainly no large variation in solar luminosity. If luminosity changes a factor of 2, we would know. We don't see this in geological record. But if changes are on the order of a few percent, we wouldn't see this on the Earth because terrestrial climate system is very complex, so there are many feedbacks. It is not easy to figure out and to read this in geological record, and in principle it is possible. Astrophysical models don't predict any characteristic time scales longer than 11-year cycle. But maybe astrophysicists didn't look at this carefully enough. Observations of solar-like stars don't give any hint, but again, we don't have observations which would be long enough and accurate enough. So in summary, variability at 1% scale is not excluded. We need to keep this in mind. However, there are no positive indication of this, so we won't consider this and invoke this as explanation for climate change.
Misha, before you go on, I'm a little confused on how you consider then the hypotheses for snowball Earths within the context of what you just said. What do you consider the trigger to be for snowball Earths? What do you consider to be solar variability?
First, it is a little before. Then, okay.
Before what? It's a little early in Earth's history, you mean?
Earlier than 500 million of years, as I remember. Is this correct?
Yeah. Last one, 700 million. Before that.
Okay. Actually, the reason for all these thoughts about snowball Earth is internal feedbacks in the climate system. You need some trigger. It may be something. It may be impact. It not necessarily sun variability.
Okay, so you just don't think it has anything to do with the sun. It's something.
It's not convincing that sun variability is responsible for this. Models say that you can do this just from internal positive feedbacks in terrestrial climate system. So the next item in this list is discrete events. Events like large impacts. What they can do? They can produce strong, short-lived influence on the climate systems. So intensive volcanic events, water outflows, large impacts release much water into atmosphere, especially if it occurs at water-rich surface, and there are many water-rich surfaces on Mars. Water vapor can produce short-lived greenhouse effect. You can expect plenty of frost, snow everywhere around the event and over the whole planet. You can expect stronger winds. You can expect increased dust load of the atmosphere, and so on and so on. These events can be pretty energetic, and What is the inventory for this in the late Amazonian? We have good evidence for some large flood volcanic events. This is the source of the most of the largest one, and actually young late Amazonian age lavas cover all of this part and maybe in patches larger area. There are two young areas here and here. They are smaller, but still it is in nowadays terrestrial scale it is pretty voluminous, pretty large volume of lavas. Excuse me. It is possible that there were water outflows in this place. Morphological evidence of this can be obscured by later lavas. Some people believe we do see this evidence. Okay, it may happen. We certainly have large impacts. If we consider craters larger than 10 kilometers as significant events that can alter climate, then one of this event in average is each 1.2 millions of years. So during the late Amazonian we have approximately 500 of such events. Not exact number because this time scale is not very well constrained, but anyway, many of them. And there are climate models. Teresa Segura did some work and showed that even with 10-kilometer impact you can some short-lived excursion of climate system. And it happens. There are craters, we see them. The youngest one is on the order of 500,000 years old, probably. Zunil crater here is the youngest one. Smaller impacts can do something. They are smaller, but they are more numerous. So we should expect that this may leave some traces on the surface. Now we don't see anything that can be for sure identified as a result of such events. In principle, from terrestrial experience, we know that short energetic events are responsible for producing most of many geomorphological features. If you go to Death Valley, you see that geomorphology is shaped by flowing water, by flash floods. So they occur not every year, they occur pretty rarely. But if they occur, they change the surface, so you see the changes. Actually, more or less of the same occur here in these mountains. Probably this is the case for Mars too. We can speculate that recent gullies of Mars, things like this, may be due to these very short climate excursions when you have warm atmosphere, humid atmosphere for very short time. Morphologically, they are very similar to gullies that are produced by energetic debris flows. There are many types of gullies on this planet. The most similar morphologically are produced by rare energetic events. Maybe this is the case. Next part of the story is internal instabilities of the climate system. There are no some a priori thinking why these instabilities should be the case. But we do see some observational evidence for this. The strongest observational evidence is so-called Swiss cheese terrain. This is southern perennial polar cap of this thing here next to the southern pole of the planet. This is a few meter thick layer of solid CO2 with some admixture of water ice in a known proportion. It produces these interesting, beautiful features. Illumination here is from upper left, so all these are depressions. And these scarps retreat with time. We see these changes in real time. In images taken year by year at high resolution from the orbit, we see that these pits, these depressions grow. And you can trace here, in many other locations in this pair of images, 1999 to 2005 here. Look here, for example, and okay, many examples. So they change. If you extrapolate observed retreat rate back, you will find that these things were initiated about 200 years ago. This time scale is smaller, shorter, orders of magnitude shorter than the shortest time scale of astronomical climate forcing. So something that initiated formation of these pits is a result of some other climate instabilities. We don't know forcing any force that make climate system change. And this should be very sensitive to climate because actually this material is in dynamic equilibrium with seasonal deposition and removal of CO2 frost. There is this work by Peter Thomas. He recognized he analyzed geomorphology of all these things in great detail, and she recognized two deposition events. So you kind of see that this mesa is kind of different from this material between pits. And they are related to two different deposition events. They also are a few hundreds years ago, before initiation of the pits, but again, pretty recently. And this says something about change of the climate system. They speculated about this change in solar luminosity in 1550. They speculated about some instability related to frequent or infrequent global dust storms, and so on. Anyway, there is a big chance that there was no such deposit 500 or 1,000 years ago. And if this deposit was absent, the whole climate system would be pretty different from what we observe now. If this deposit is absent, this means that some ice that we know is beneath this deposit, water ice, is exposed to the sun. And summers in southern hemisphere are much warmer than summers in northern hemisphere because Mars is closer to the sun at this moment. This means that sublimation of this ice is more intensive during summertime, and total water content of atmosphere is significantly higher than we have it now. And we can expect some minor deposition of frost, nighttime frost, seasonal frost of water. We can expect some other different things, so the whole climate system works in different way. For example, we can speculate that recent gullies may be formed by deposition of small amount of frost in alcoves and springtime melting, for example. Calculations show that this is marginally possible. Another thing that can be related to this wetter, very recent climate is related to these maps. So this is hydrogen content in upper meter of Martian surface derived from neutron spectrometer data. Warmer shades means higher water content. There is plenty of water at high, this is from 60 to 60 degrees latitude, the whole planet. Higher than 60 degrees, there are plenty of water ice in the ground. In these patches, it is up to 10 weight% of water equivalent, which is not plenty, but it is much. And one of ice here is not stable currently. And one of explanations why we see this signal by Bruce Jakosky is so that 1,000 years ago, when the atmosphere was warmer, was wetter, ice was stable here, and it was present in the soil, and now it goes away, but still there is something. So maybe these are the traces of this result of internal climate instability of short time scales. Now we come to the most interesting, the most well explored, the most complicated part of this story. This is astronomical climate forcing. This is evolution of eccentricity and obliquity, eccentricity of the orbit and obliquity of spin axis of Mars for last 10 millions of years. It is calculated pretty accurately. So this is 10 millions years ago. Green is eccentricity, you see these oscillations. Black is obliquity. On the Earth, similar oscillations occur, but they are 2 orders of magnitude smaller. On Earth, they actually change of season of perihelion is thought to be the trigger for ice ages. But it is only a trigger. The actual reason of ice ages is internal feedbacks in the climate system. On Mars, this forcing signal is very strong. So it can be driver of climate, not trigger of climate change. Not maybe, it is. These plots show summertime insolation of high-latitude high-latitude areas. So this evolution is well calculated for the last 10 millions of years. It is not possible to calculate it exactly for periods of time longer than 20 million years because of chaotic nature of solar system dynamics. It is not predictable in principle. If we enhance our knowledge, enhance accuracy of our knowledge of planetary characteristics by order of magnitude, we can go back in time by 1 million of years. 1 order of magnitude, 1 million of years more. There is no way to calculate it back and back in time. These are model calculations for 250 millions of years. Each of this plot is different calculations. They are different from each other in minor change of one parameter characterizing planet. This minor change is well within accuracy at which we know this parameter. So you can consider this as examples of possible scenarios of change of obliquity for the last 2.5 millions of years, but we don't know what happened. All of this starts from these oscillations like this. These oscillations persist through the whole history. But look, here the oscillations are about 25 degrees obliquity, and here oscillations are about 35 degrees obliquity. And to this several million times scale variation of mean obliquity value, it is not predictable. It can be of any kind. This table lists the shortest periods of all these oscillations. They are tens of thousands of years, hundreds of thousands of years. So characteristic time scale related to these oscillations are 7 times shorter, and large scale variations of eccentricity is 0.4 million of years characteristic time scale. What I was interested to do is to look at the very beginning of all these histories. So this is the first million of years. This is obliquity. For last third million of years, obliquity changes just a little. It is not very strong signal. These two curves are insulations of northern and southern poles in summer. And here these variations of insolation, they're significant, and they are controlled by season of perihelion, change of season of perihelion. And I try to look for some signal in geological record on Mars where I can see this hemispheric asymmetry that would be related to this difference in this signal. And I found some very interesting phenomenon. I will tell you now. It is reported at LPSC this year, not published yet. So I and a number of my students, we looked at patterned ground at high latitudes in both hemispheres on Mars. It is more or less terrain where Phoenix lander landed. You see example here. These craters are 12 meters in diameter. But they are very small. It is very very high resolution image. We took 10 okay, this slide from LPSC. Now we have more images and higher areas. Principal result is the same. At high latitudes, we look for all craters, small craters there. You see examples of small craters. There are actually few of them. If you take an image, it is real work to find one. If you just take arbitrary image, put it on your screen, you won't see a crater at all. Now we have a few hundred of features like this. And in many cases it is difficult to say what is crater, what is not a crater, but there is one subclass of craters that we call sharp craters, features like this. They are well seen. They have kind of sharp break and slope when we go from surrounding terrain into crater, unlike this one, like this one. They are in pairs here because the projectile broke in atmosphere. So this is the same impact event, just two pieces of the meteoroid. And we can identify this object. If they are larger than 5 meters, we can identify them reliably and with certainty. We can count them. This is size frequency distribution. It is steep. Okay, I won't go into detail of crater counting technique. But we can assign some age to this population. Absolute calibration of this age is pretty uncertain. We can say that this age is somewhere between 10 and 50 thousands of years. So you can think that you need about on the order of 5,000 Martian years to convert this sharp crater into this smooth crater. All this is for the southern hemisphere. When we look into the north hemisphere, we see almost nothing. So far we found only 3 craters and 6 images that I worked through after LPSC didn't give me any one more. Statistics is not good. 3 craters is not a good thing for statistics. But anyway, it is obvious that effective age of this population is at least an order of magnitude younger than the age of this population. So this transition from sharp craters to smooth craters in northern hemisphere is significantly quicker. When we turn back to this plot, so this is enlarged plot of the same thing. With all uncertainties of crater counts, with all uncertainties of statistics, our age of population in the northern hemisphere is somewhere here. So we are certainly at the present day spin orbit configuration. And this is a situation where effective smoothing of craters occurs. This is a very wide range of possible ages for this population in the southern hemisphere. It is reasonable to suggest that we deal with the same, not with symmetric, with mirrored spin orbit configuration, when summers are warm in northern hemisphere and cold in southern hemisphere. So effective smoothing of craters occurs when summers are cold and winters are short. So this looks like the signal related to this time scale of climate change. Identification of difference in crater age is very reliable. And my favorite explanation that here we have some minor migration of water from one hemisphere to another hemisphere. It should be effective if we don't have this CO2 deposit on top of the southern polar cap. Then there is a possibility, and there are models that show this, that there is significant migration of water from hemisphere where summer is warmer to hemisphere where summer is colder. So maybe this smoothing is just deposition of some thin mantle of icy material, and this is what we observe. I skip the logic why we can reject some other explanations. Now let's turn to longer time scales, what we can see at high obliquity. From first principles, what we can expect from high obliquity if obliquity is high. This means that seasonal changes are more expressed. Severe winter is expanded to lower latitudes, and summer is much warmer. So this amplitude of seasonal changes of weather is much more significant. And this means that terrains at high latitudes that contain much ice, we know this for sure, they are exposed to much higher summertime temperatures, and we can expect more water vapor in the atmosphere. And finally, if obliquity is high enough, we can expect migration of water vapor from higher latitudes to lower latitudes and deposition at lower latitudes. And climate models can reproduce this logic, and they indeed, I put works by Francois Farget here, and as I understand, Bob Haberle has this in his models too. Kind of pivot number of obliquity for this switch is about 35 degrees, but it is not actually a function of obliquity, it is function of summer insolation. Do we see this in a geological record? Let's see. For decades, people wrote that polar layered deposits contain a record of past climate changes. These are very nice, plenty, hundreds, thousands of layers. This material is mostly ice. This in the northern polar layered deposits here. It is certainly climate related. It certainly contains a record of climates. We cannot read this record. Many people thought about this. I tried, many other people tried. We don't have any good solution for this. Maybe the most successful attempt is this work by Leverard et al. They tried to model this migration of ice from polar regions to tropics and back. So according to the model, when obliquity is high, so now this is the same obliquity plot upside down. So now is here, 10 million years ago is here. And when obliquity is oscillated about 30 degrees, ice cannot stay here. It resides, according to the model, mostly here in western slopes of high mountains. When obliquity start systematically decrease from these higher values to these lower values, there is migration of ice back and forth from here to here and back. At some moment somewhere here, ice migrated here in low obliquity period, has no time to go back at high obliquity period, and we start accumulation. And this is a result of one of their model runs where you have deposition of layer by layer from here to here. So these layers reflect more or less of these oscillations of obliquity. So this predicts existence of layers. Well, and we can excuse me, we can think that the total number of layers in this way can be more or less total number of oscillations somewhere from here to somewhere here. But authors of this paper just don't know that there are images where you can see just right number of layers. So it is 20-something here, this is 20-something here. This is located here at the head of Casma Boreale. This is one of few very steep scarps in the polar layer deposit when you have the whole record in one very steep exposure. It is not obvious here, but this is the floor of this. So this is low, this is high, this is flat, this is flat, this is almost 45 degrees steep slope, almost 2 kilometers high. And surprisingly, total number of layers here is more or less consistent with total number of oscillations here. It looks like there is something reasonable in this model. We have reasonable consistency. Well, the model predicts existence of ice here at periods of high obliquity. Let's look what we see here. We see geological record of the presence of ice. This is not my work. I just tell story from other works. All these deposits are here. They are large. They occur at flank of Arsia Mons. So caldera is somewhere here in this scale. These are moraines deposited by cold-based glacier. This is not morphology usually seen in glaciers on the Earth. But this is because climate on Mars is very cold. On the Earth, usually glaciers slide on top of slide on the substrate because their thickness is limited by melting at the base of the glacier. Such melting does not occur on Mars because it is too cold and it is frozen to the ground, and there is no strain just at the ice substrate interface. Morphologies are different, but they are known in some locations on the Earth, and they are similar. So these are moraines that are left by the most distal advance of the glacier. This is younger deposits. They may contain some still contain some ice. We see similar deposits on all four mountains. This is example from Olympus Mons here. They are here and here too. Morphology says that these deposits used to be very thick. Ice flow models say that this deposit used to be very thick. If we do rough volume calculations, these glaciers can accommodate the whole volume of ice in polar caps. So the story looks consistent. Then models say that time scales of development and evolution of such glaciers should be long, so you need tens of millions of years for this morphology to form. This means that you necessarily need prolonged periods of high mean obliquity. So everything is consistent except the age. These deposits are too old. They are much older than 5 million of years that predicted by that paper by Levrard et al. Dave Sheen did some age estimations for here in RC. Unfortunately, he didn't publish this. He has significant difference in ages here and here. So youngest age is somewhere here. Maybe more or less consistent given all uncertainties in age determination technique. But it is only here in small area, and then you have problems with volumes. So there is no perfect consistencies in all this story. In principle, it is possible that you can deposit much of ice more or less quickly and remove it more or less quickly, and it leaves nothing in geological record, but these are so well preserved and expressed. It looks like if it were the case, we would see some very late episode. We don't see this in geological records. So there is no good consistency. Maybe these mountain glaciers are related to some more or less prolonged period in old Mars history, something like this. We don't know. And with all this, all the story with layer terrain is not known very well. Another interesting features are lobate debris aprons, lineated valley fill, and concentric crater fill. These pictures show all three. These are very typical lobate debris aprons. You see a mountain here. It's pretty high, about more than 1 kilometer high. And this is 100.5 meter thick, convex shaped deposit. Such deposits we know now they contain much ice. From radar data we know this. This is of the same deposit. It is not as typical as this, but still it is of the same thing. A similar material is here in the valley. This is lineated valley fill. And these are not very typical, but crater fills. So probably recent analysis show that they are the same phenomenon, just geometry is different. They occur everywhere at mid-latitudes. There are plenty of them here, where climate models predicted deposition at high obliquity. There are plenty of them everywhere, in many places at mid-latitude of the planet. Climate model are not readily predict them, but you can tune knobs in climate models. You can make ice deposit out there. There are many questions related to this. So it looks like this ice, they are related to ice. They look like glacier-related deposits. It is not clear what is the relationship between tropical mountain glaciers on one side and lobate debris aprons on the other side. Are they formed at the same time or not? Are they related to the same obliquity excursion or not? Maybe you need to, maybe some of them are related to some release of underground water, major release of underground water to the surface. It is not known what is responsible for strong difference in morphology between them. Dating techniques are not, okay, all this cratering stuff Craters are bad. It is icy material. Craters are not well preserved on these deposits. It is very difficult to count craters on them. So cratering techniques do not work very well. So it is different to figure out are they contemporaneous or not. So there are many questions related to this. Certainly they are indications of different climate. Probably they are indications of long period of high obliquity. But we don't understand this well enough. Then, of course, I can't help. I want to show this picture once more. These are recent gullies. We can think about recent periods of high obliquity to explain these gullies. And high obliquity can help in two different ways. One way of logic, at high obliquity, summers are warmer, atmosphere is wetter because we evaporate more from polar caps. This produces some change for winter time, minor accumulation of snow or frost in winter time. This produces some chance for springtime, daytime melting. This may produce minor amount of water that carve these things. We can speculate about other way to produce these things. We can think about somewhat high obliquity when summers are even warmer, and then day average temperature can climb above freezing day average temperature. This means that there is thawing of upper layer of frozen ground, and we can produce all this wet debris that can carve these gullies. So there are two ways to produce these features. Plus, we already saw two other ways that can produce these features. So my conclusion is that at our current understanding, origin of these features is not very well constrained. They are related to recent climate change. So they are recent. They are not formed presently. But we don't know what climate change. Okay, I will skip this. So we are close to conclusion. I gave some overview of forces that control recent climate. I showed not all, but a few examples of what we see in geomorphology. And I leave this as a question if we can reconcile one and another. So this work, it is very interesting. It looks kind of promising, but it is still very far from the end. Thank you.
Hello, thank you for the talk. I was wondering where you mentioned that you thought that the drop moraines on Tarsus Mountains, that they had an age of greater than 500 million years. Where did you get?
The number is
That's the constraint there, 60 to 200.
60 to 200. So this is more or less ages for old parts of these deposits. Younger deposits here are probably somewhat younger.
Okay.
This is from work of Dave Sheen.
I thought I heard you say that it must have been 500 million years old.
No.
Huh?
It doesn't agree.
5 million is what you want, and
5 million is what
yes, I
yeah.
see. No, I'm in agreement with this actually, because I don't think you can get ground ice forming in equatorial regions until you have obliquities in excess of 45 degrees, more like 55. Is what I think. Of course, the altitude of the mountains helps a lot.
Any other questions?
So they've observed on the two rovers that occasionally the wind will blow the dust off the solar panels, the local atmosphere. And I was wondering, did that occur in the summertime at either of the poles? Because you talked about how ice would sublimate and migrate, right? So do they know when those events occur?
I don't understand.
So early on, they noticed that the power levels went back up
Yeah.
because the dust had
yeah,
been
there
blown
is dust
off,
removal
right?
from rovers.
Right.
Yes.
So there was a. So, do they know when did those occur? When it was summer? Because you talked about the migration from southern to northern, right? So did you have greater winds during that period that would cause that, or do they know when those events occurred?
I was speaking about migration of water from place to place. When it is summer, ice evaporates, sublimates, and there is increased amount of water vapor in atmosphere. It is very small amount. It is not related to lifting of dust with winds. Winds are, okay, there are winds, so they move dust. Sometimes there is plenty of dust in atmosphere. In terms of mass, it is more dust than water vapor in atmosphere.
Misha, just a comment and a question. The comment is that most of your discussion about the processes that form the gullies are related to stuff coming out of the atmosphere and melting on the surface. But there are a large number of people who have been advocating for subsurface aquifers and releasing water in that way, and that's a completely different mechanism that's not necessarily connected to climate change. The question I have for you, though, is, as you know, the Odyssey spacecraft has detected large amounts of hydrogen beneath the surface at latitudes above 40 degrees or so in each hemisphere. And I'm just wondering if you've seen anything in the geological record that can provide us clues on how that water actually got there and if it actually moves in and out in some fashion as well.
About first part, yes, many people speak about groundwater discharge. I don't believe in this story because there are many arguments against that. Gullies are formed in isolated mesas, peaks, massifs, and it is very difficult to have pressurized aquifer there. And if you calculate temperatures in the ground, it is very difficult to have aquifer there. So I personally don't believe in that. About your question, you speak about high latitudes, like Phoenix landing site, and my impression from geomorphology that we deal with deposition of icy layers. I see many evidence of layered structure of this material in places. This degradation of impact craters looks consistent with deposition of half a meter of material on top. In other places, we see things that looks like deposition. We see very fresh deposits of ice in some rare places at very high latitudes in some crater walls. Just bright icy material, it is spectrally ice. Unfortunately, I don't have an image. So we see this signal in roughness signature, smoothing of everything. So I believe that all these deposits is ice deposited from atmosphere as snow or frost through all these climate changes and migrations from hemisphere to hemisphere, from low latitude to high latitude, from pole to mid-latitude, from mid-latitude to pole, and all these things.
Misha, another type of geomorphology that's sometimes associated with, at least on Earth, it's associated with paraglacial landforms and climate change in that respect, are pingos. And a survey of pingos on Mars, they've been hypothesized to exist from the equator up to the poles, suggests that the most viable candidates for true pingos, which are I should define my terms. That's an ice core deposit on the scale of maybe 100 meters in diameter. That the most viable candidates are in the mid-latitudes, kind of in the area where you've done a lot of your work. Have you seen anything in your work that you think is a viable population of pingos? And does that influence your thinking at all?
I didn't look at this especially. Yeah, I have my opinion on this.
I just had a quick comment. You mentioned that the gullies on central peaks could not be formed by aquifer theory or anything like that, and that's quite likely true, but it doesn't mean that gullies that were formed on central peaks are the same mechanism that were formed classic gullies or sand dune gullies, etc. So I just want to make that comment that you can't rule out the aquifer theory just from one type of gully system.
Yeah, on one hand, I agree that there are gullies and there are gullies. They are different, I agree. But in general, I looked much at these features, and I have strong impression of that many of them are related to some melting, to some surface processes related to some melting. I don't exclude possibilities of that somewhere there are some features. Actually, many of them are similar morphologically. Maybe there are different classes. But generally, my vote for melting in one or another way.
As a token of our gratitude for Misha for making the trek up here from Santa Cruz, we're going to give him a little SETI Institute pin. And let's thank Misha again for his very good work.
Thank you.